This is the Conceptual Physics Chapter 2 Homework Assignment Solutions Guide. Question 21. In the graph shown here, velocity is plotted as a function of time for an object traveling in a straight line. So, question A. Is the velocity constant for any time interval shown? Explain. So, is the velocity constant for any time interval? The answer is yes. The velocity is constant from 0 to 2 seconds. Now, to explain, the graph during that time is a flat horizontal line, which means it's not changing in terms of its velocity. The velocity is constant for the first 2 seconds. During which time interval shown does the object have the greatest acceleration? Recall that for a velocity time graph, acceleration equals the slope. So where is the slope the greatest? That would be from 2 to 4 seconds. So from 2 to 4 seconds. That segment has the greatest slope and therefore the greatest acceleration. Question 24 says a car moves along a straight line section of road so that its velocity varies with time as shown in the graph. I've got a picture of the graph right there. A. Does the car ever go backwards? So this is a velocity versus time graph. If the car was going backwards, we would have to have a negative velocity. If this on the graph is our 0 point, then at no point is the graph below 0, so the answer is no. The velocity is always positive. B asks, at which of the labeled points, A, B, or C, is the magnitude of the acceleration greatest? Explain. The magnitude of the acceleration, that means we don't worry about whether it's positive or negative. We don't care if the slope is up or slope is down. We just want to know where is the slope the biggest. Since these are all equivalent time intervals from 2 to 4 to 6, we can see that section A has the greatest slope. All right, on to the exercises. Exercise number 1. A traveler covers a distance of 460 miles. Oh, let's erase that. $460 miles in 8 hours. So that's our time equals 8 hours. What is the average speed for the trip? So average speed is going to equal the distance traveled divided by the time that it takes. So there's 2 different ways we can do this. We can just plug in our numbers right now that we have, distance and time, 460 miles in 8 hours. And when we do the division, 460 divided by 8, that gives us 57.5 miles per hour. Great. So that is one method. If you took, we'll call it the more physicsy method, and converted your units into metric, doesn't ask you to do it, so I'm not going to require it, but this would be doing it the more physicsy way. You would convert your miles into either kilometers or meters, your time into seconds, and you might come up with 25.7 meters per second, and that's an acceptable answer as well. Exercise 5. A woman walks a distance of 360 meters with an average speed of 1.2 meters per second. We're asked to find the time it takes her to walk that distance. So we know that speed average speed is going to be the total distance divided by the total time. So we want to take this equation and solve it for time. So I'm going to multiply time up to the top. So the time is going to cancel out. I'm going to divide by speed. Divide by speed. And speed divides out. We're left with, on the left-hand side of our equation, time. And on the right-hand side, distance divided by speed. And we know the distance and we know the speed, so we can solve for the time. Time is going to equal 360 meters divided by 1.2 meters per second. And if you're clever, you'll notice that the units do work out. Dividing by meters per second is like multiplying by seconds per meter. The meters divide out, we're left just with seconds, so that's perfect. The answer is going to be 300 seconds. Now that's fine. If you answered 300 seconds, great. You might also have converted that into minutes. You can multiply by a conversion factor. 60 seconds is equal to 1 minute. 300 divided by 60 would be 5 minutes. So either 300 seconds or 5 minutes, either of those is a perfectly valid answer. All right, exercise number 7. A hiker walks with an average speed of 1.2 meters per second. What is the distance in kilometers that he can travel in 1 hour? Time equals 1 hour. All right, so we have speed in meters per second. We have distance that we want to have in kilometers, and we have time in hours. So we're going to have to do a couple conversions so that everything is speaking the same language. I think the easiest way to do this would be to go from meters per second into kilometers per hour. That way, when we multiply by our hours, the hours will cancel out, and they'll leave us with kilometers in the end. So how do we get from 1.2 meters per second into kilometers per hour? We got to use a conversion factor. So I know that 1 kilometer is equal to 1,000 meters. So then the meters will divide out. Now I've got to go from seconds to hours. I know that 1 hour is 3,600 seconds. The seconds go away, and what's left? Kilometers here and hours here. Great. So 1.2 multiplied by 1 multiplied by 3,600 divided by 1,000. So we end up with a speed of 4.32 kilometers per hour. Awesome. I know that speed is the distance divided by the time. I want to solve for distance, so I multiply time up to the top, time goes up to the top. Distance is going to equal speed times time. Speed times time, so it's 4.32 kilometers per hour times 1 hour. That tells me that the distance that he can travel is equal to 4.32 kilometers. All right, exercise 11 now. Starting from rest. Okay, so that's the first part of the sentence, but it gives us information. Whenever you hear starting from rest, we know the initial velocity is equal to 0 meters per second. A car accelerates at a rate of 4.2 meters per second squared. So the acceleration is 4.2 meters per second squared. Outstanding. And it says it accelerates for 5 seconds. Time equals 5 seconds. What is the velocity at the end, or the final velocity? All right, great. So I know we've done this in class, but I'm going to take you through the where this equation comes from. Acceleration is change in velocity divided by change in time. Change in velocity is final velocity minus initial velocity, and we're dividing that by the amount of time that goes by. I can multiply the time up to the top, and that cancels out. And since I'm trying to solve for final velocity, I'm going to add initial velocity, which is being subtracted here. So I'm going to add that to both sides. V initial. That leaves us with an equation, so that subtracts out. Leaves us with an equation for V final. It's equal to everything left on this side. V initial plus acceleration times time. Well, I know V initial is 0, because there it is right in the given information. So V final for this case is going to equal our acceleration, 4.2 meters per second squared, multiplied by our time, 5 seconds. That gives us an answer of 21 meters per second. Exercise 13, a car traveling with an initial velocity of 14 meters per second. So V initial, it actually has an initial velocity this time, unlike the last problem. And the initial velocity is 14 meters per second. Accelerates at a constant rate of 2.5 meters per second squared. So acceleration equals 2.5 meters per second squared. And it's going to accelerate for a time of 3 seconds. What is the velocity? So part A is asking, what is the velocity after this time? So after implies final velocity. V final is what we're trying to find. In the last problem, we came up with the equation V final equals V initial plus acceleration times time. So we know the initial velocity is 14 meters per second plus the acceleration is 2.5 meters per second squared times 3 seconds. Sorry, I'm running off the page a little bit. You can plug those numbers in, and you get a final velocity of 21.5 meters per second. Great. Part B asks us to find the distance traveled during that time. Looking at our other equations that we have, this tool up here, it doesn't work for this. There's no distance involved, but we do have a distance equation for an accelerating object. Distance traveled for an accelerating object is going to equal V initial times t plus 1/2 AT squared. And we know all of those things. The initial velocity is 14 meters per second. Time is 3 seconds plus 1/2 the acceleration, 2.5 meters per second squared, times the time, 3 seconds squared. When we plug all of those numbers in, we'll find that it has moved a distance of 53.25 meters. Exercise 15. A car moves with an initial velocity of 28 meters per second. So V initial equals 28 meters per second. And slows down at a constant rate of -3 meters per second squared. -3 meters per second squared. We know speeding up is an acceleration, but slowing down is an acceleration too. So we know its initial velocity, we know its final velocity. Sorry, we know its initial velocity, and we know its acceleration. That's what's given in the problem. Part A says, what is its velocity? What is its final velocity after a time of 4 seconds? Time equals 4 seconds. So we're going to go back to our V final equation we've been using. It's going to equal V initial plus a times t. V initial is 28 meters per second, plus acceleration is -3 meters per second squared, times t of 4 seconds. And we're going to find a final velocity of 16 meters per second. Does that make sense? Yes, it was going 28 and it slowed down for 4 seconds, so it's going to be going slower. All right, part B of this problem says, what distance does the car cover in this amount of time? Well, it may seem more difficult. This is no more difficult than the last problem that I asked you to do, number 13. The only difference is that we have negative numbers to deal with, but they just go in the equation just like they did before. Nothing changes. Distance is equal to v initial times time plus 1/2 a t squared. So v initial is 28 meters per second times 4 seconds plus 1/2. The acceleration is -3 meters per second squared times time, 4 seconds squared. When you plug those numbers into your calculator, you should find a distance of 88 meters traveled. Answer 1, answer 2. All right, on to number 17. Exercise 17. A world-class sprinter can run a distance of 100 meters, starting at his top speed of 11 meters per second, and running with a constant speed throughout. How long does it take him to cover this distance? So how long means time. This goes back to the same process we did at the beginning. It says running at a constant speed throughout. Constant speed means the acceleration equals 0, which means we can use our definition of speed. Average speed is equal to distance traveled divided by the time. Again, we're going to multiply the time up. We're going to divide by speed. So that divides out. That leaves us with a time equal to distance divided by speed, which is equal to 100 meters divided by 11 meters per second, giving us a time of 9.09 seconds. All right. Last but not least, SP, synthesis problem number 2. The velocity of a car increases with time as shown in the graph. So I tried to copy down the graph. It's not as neat as the one in the book, but you can always look back at the one in the book if you get confused by my drawing. But I get the key points here. Part A is asking what the acceleration is. This is a velocity time graph. So it's asking the acceleration from 0 to 4 seconds. Acceleration of a velocity time graph is the slope. We see that it is going up 4 meters per second. It's going over 4 seconds. So the slope of that graph during that spot is going to be 4 meters per second divided by 4 seconds, which is 1 meter per second squared. Part B says find the slope, find the average acceleration, which is the slope, from 4 to 5 seconds. So from 4 to 5 seconds, it's going to go, I'm going to switch to blue here, it's going to go up from 4 to 12 in the velocity, so 4 meters per second up to 12 meters per second, which means that I have a change in velocity. Delta V is equal to 8 meters per second, and that's going to happen in a time of, it's going over 1 second. So 8 meters per second happening in, a change of 8 meters per second happening in 1 second means an acceleration of 8 meters per second squared. C, what is the average acceleration between 0 and 5 seconds? So I'm going to go to green, and I'm going all the way over from 0 to 5. And I have a change in velocity. So acceleration equals delta v over delta t. I have a change in velocity of 12 meters per second, and it happens over a 5-second period, which means for part C I have an acceleration of 2.4 meters per second squared. Great. All right, part D is more conceptual. It says, is this result in part C equal to the average of the results in part A and B? The average of parts A and B would be halfway between 1 and 8. And halfway between 1 and 8 is bigger than 2.4. So the answer is no. It isn't the same as the average. Now, why would that be? Well, I am traveling at with a lower acceleration for the first 4 seconds. So I have a smaller slope for a longer amount of time. I have the big slope, the 8 meters per second squared slope, only for 1 second. So when I average the two, I'm spending a longer time with an acceleration of 1 meter per second, so it's going to have more of an effect on the average. All right, that's your solutions for your homework. If you have questions, please come see me and ask. Otherwise, have a great day.